In this screencast, I'm going to show you how to create a tool for analyzing the results of data you've collected. You want to come down a couple rows to begin with, and to say row A3, and I'll give it a title, and I'll call it trial number. And of course, the first trial is 1, and we want this to count in succession. Now, we could type all of the numbers, but that's a waste of time when we have a tool like this. We can get the spreadsheet to calculate those values for us very easily. In fact, every cell that you see on this spreadsheet is a calculator. So when I click on column A, row 5, which is a cell that's blue highlighted, I'm going to type the equal sign. I'm saying perform a calculation for me, spreadsheet. I want it to be equal to this cell plus 1. And I hit enter. And you might say, well, that's not going to save time. It would be faster to type the numbers. But here's where it gets quicker. When I click on this cell, there's a little blue box right here like so. And when I click on it and drag it down, it will modify that formula and send the calculations downward for me. The next thing I'm going to do is paste in some data that was shared to me by our class. Those happen to be the data values that were shared with us. So the first thing I want to do when there's collaborative data, and we've spoken about this, is to examine the data. What I notice here is that this one value doesn't agree with significant digits, and as we discussed in class, this has to do with the formatting of the numbers. So I'm going to highlight this column, and I'm going to format the cells so they go to the hundredths place. And I can do that with clicking those buttons or to format the cell number. All right, so we have the trial number. In this case here, let's call this the width. And I put in my units. But there's more information I want to record. So I'm going to take this and move it upward like so. And the first thing I'm going to do here is record the reading error. Now, let's assume this was collected with an analog device. So I would hit plus or minus 0.05 centimeters. And I hit return, you'll notice I get an error. And that's because it thinks I'm trying to do a formula. The simple way to fix that is to put a space in front of it, and then it recognizes it as text. The next thing I want to do is move this down a little bit more. So I am going to insert cells with the insert menu, and I will call this the total estimated error. I will widen the column again. And the total estimated error, since we've talked about how to estimate this, let's suppose it's used with a regular ruler, in which case it would be double. So plus or minus 0.10 centimeters. And there we have our data, like so. All right, so I've got the data like this, and I want to compute a whole bunch of statistics. So down here, the first thing I'm going to do, which makes sense, is the mean. And I would want to find the maximum and the minimum and the range, the absolute uncertainty, and the percent uncertainty, the count, the upper limit based on these statistics, and the lower limit. Now those are absolute uncertainty-based statistics. We're going to use population-based statistics via normal distribution down here as well. So what we need for this is the standard deviation. We need twice the standard deviation. Which we call the data error. And then what we would have is our upper limit. and that's what is a 95% confidence. Then we might have our mean, and then we have our lower limit with the 95% confidence interval, like so. So now we would calculate these. The mean, the formula we use is equals average, and we highlight all the numbers, like so. That gives us the mean. The maximum is equal to the max. And I highlight all the numbers. And the minimum is equal to the min, highlighting all the numbers. And the range is max minus min, so that's equal to this minus this. The absolute uncertainty is the range, or max minus min, divided by 2. So that is equal to this divided by 2. The percent uncertainty is the absolute uncertainty divided by the mean, so times 100. So that equals this divided by the mean times 100. The count is equal to the count of all the data. What we can see here is there's 23, and that should agree with the trial number. The upper limit in this case is going to be equal to the mean plus the absolute uncertainty. And the lower limit is going to be equal to the mean minus the absolute uncertainty. So a couple things we want to do to clean this up is we need to apply units wherever they're appropriate. So the mean, 3.79, refers to centimeters. Similarly, the max and the min refer to centimeters. The range is also centimeters, varies over 0.08 centimeters. The absolute uncertainty is also in centimeters. The percent uncertainty is in percent. The count is a number which doesn't have units, and the upper limit would be in centimeters, and the lower limit would be in centimeters. So what this is saying is that based on the data we have in computing this, our upper limit is 3.83, and our lower limit is 3.75. You notice those happen to agree exactly with the maximum and the minimum. When we calculate them, they may not come out the same, but basically the meaning is the same, that we are looking from the smallest to the largest values. Now, why do we compute the second set of statistics? Well, it's because we can't just consider every data point. There may be outliers in our data, and so there may be some extreme values that represent a very small distribution, a very small frequency of occurrence. Some outliers that just don't represent the data, and we want to exclude those. And the way we do that as scientists objectively is through the standard deviation. So equals STDEV of the data. Highlighting numbers, boom. So if you notice, when I'm starting to look at these numbers here, they all pretty much seem they need to be to the hundredths place except this count. So I'm going to just highlight them all right now and make them all go to the 100ths place, except this one, which I am going to take back to the ones place. So standard deviation is 0.03, but even though it says 0.03, it remembers what the unrounded values are, and that's a beautiful thing about spreadsheets. The data error is equal to 2 times this number, and so notice that's 0.06. The upper limit is going to be equal to the mean plus the data error. And the mean is simply this number. And the lower limit is equal to the mean minus the data error. So what we have here is when we look at the max-min statistics, we're saying that the data ranges between 3.75 and 3.83. When we do norm-based statistics, bell curve and normal distribution-based statistics, we see it's 3.73 to 3.85. So in other words, what this means is that the data is actually more spread out. The data tends to be outliers. When this